Hi everyone. In this video, I'm going to sort of preview what's to come for the rest of the semester, so for the final third of this class. Now, the final third, in my opinion, is going to be the most exciting part because that's when we get to really the new stuff, which is going to be Lagrangian mechanics. And this we'll see is really a new way of approaching the same problems we were solving before, but we can solve much more complicated ways in a way that I think is actually easier. And I think it's interesting because it's an entirely different approach. And really, this sort of approach in modern times is thought of sort of as more fundamental and ultimately is more far-reaching into different fields of physics. So especially if you go into graduate school, this way of thinking about classical mechanics is really going to be the way that you want to think about it. So I just want to briefly touch on sort of a few new words that you'll be seeing, and I just sort of want to let you know how we're going to move through learning these new ideas, because I'm going to stray a little bit from the order that the textbook goes in. And I'm going to start, so next should be chapter 12 of the textbook, but I'm going to start with chapter 13 and then sort of go back and forth between chapter 13 and chapter 12 and then proceed on to chapter 14. But I'll try to be real clear with you so you always know where we're at. So the first new word that you need to know is the Lagrangian. So the Lagrangian is really going to be our primary quantity of interest. Now here I say that it's a scalar function associated with your system, and often you can calculate it by simply taking the kinetic energy minus the potential energy. Now, not all systems have well-defined potential energies, right? If we have a system with non-conservative forces, right, we know that we can't define a potential energy if we have forces which are non-conservative. But we'll see that there are still going to be ways to write the Lagrangian in these cases. And really, when I think about the Lagrangian at the end of the day, and especially when you move on to more advanced fields of physics, I think of the Lagrangian as a function that really just defines the system that you're dealing with. It encompasses everything that you'll need to know. It includes all of the interactions that you have, so ultimately all of the forces that you have. So really, in modern physics, you think of the Lagrangian as like the defining function of your system. Now, from the Lagrangian, you could calculate something known as the action, which is a functional, which is really just the time integral of the Lagrangian. Now, what is a functional? So this S of Q, where I'm writing it in brackets, and why am I using these sort of squared brackets? That's common notation to denote that this is a functional. Now, what is the difference between a function and a functional? Well, this argument Q here is a function itself. So a functional is a function where your input is a function, right? A normal function has just a single variable as your input, where a functional, your input itself is a function, but then ultimately, when you put a function into this functional, it spits out a normal number, just like a function. You put in a variable and it spits out a normal number. And so this action is simply the time integral over our Lagrangian. And why do we care about the action? Well, we care about it because of something known as Hamilton's principle, which says that the actual trajectory of a system is given by some path which extremizes our action, right? So it makes it a stationary point. So it's either maximum or minimum, or it's some flat surface. Most of the time it'll often minimize the action, but that's not always going to be the case. So Hamilton's principle tells us that if we compute this action, where the action again is the integral of the Lagrangian, and the Lagrangian is a function of these Q's, which Q's I'll say are going to be generalized coordinates of our system. right? So Q here, I'll remind you, these are generalized coordinates. And Q I'll add is, it's a common notation that we use for these generalized coordinates. It could be X, Y, and Z, it could be theta, but there's some set of coordinates where if you have a value for each coordinate, it completely specifies the configuration of your system. So if we take this action and we extremize it, then it turns out that the Q associated with the extremum of that action is going to be the actual trajectory that our system follows. So if we want to be able to apply Hamilton's principle, we're going to need to review what's known as the calculus of variations. So that's actually in the next videos that I'm going to post right after this one. I'm going to be talking about the calculus of variations, which really is the mathematics of extremizing functions in this way. So we're going to need to review how to extremize functions in order to apply Hamilton's principle, which is ultimately what we want to do. And then from Hamilton's principle, we'll be able to derive what are known as Lagrange's equations. And Lagrange's equations are really what we'll use to solve for the equations of motion of our system. So we can derive what are known as Lagrange's equations from this Hamilton's principle by studying how generically we could extremize an action, right? So Lagrange's equation ultimately will be a set of equations that we solve to find the equations of motion of our system. Now, really, equations of motion are the things that ultimately we're interested in. So really what we're doing is we're replacing Newton's laws with Lagrange's equations, which will give us the same equations of motions we would have derived by applying, for instance, F equals ma, but this is going to be an entirely different way of getting to these equations. And I'll say it's more challenging in that it's going to be new and it's going to feel conceptually difficult for that reason, but mathematically, Lagrange's equations are actually a lot simpler. So if you really want to solve some very complicated systems like connected Atwood's machines or something, which would be pretty complicated and mathematically difficult to solve using Newton's laws, these will be a lot simpler to solve using Lagrange's equations. All right, so after we learn about Lagrange's equations, which really is the meat of this last part of the class, this is really the main thing that we're going to want to learn how to do is apply Lagrange's equations. We'll introduce something known as Noether's theorem, which is really a beautiful, amazing theorem that tells us for every symmetry of our system, there exists some conserved quantity and vice versa. And we'll see that, for instance, in the past, we've seen conservation of energy, conservation of linear momentum, conservation of angular momentum. And Noether's theorem really teaches us that the reason we have these conserved quantities is because of symmetries that exist in our system. And we'll see that if we break these symmetries, then we no longer have these conserved quantities. And then finally, the last thing we'll do is we'll introduce Hamilton's equations, which Hamilton's equations are really just a reformulation of Lagrange's equations, but now as a set of first-order differential equations instead of second-order differential equations, but we're going to have more of them. And I'll say that generally in classical mechanics, Hamilton's equations aren't actually really better necessarily than Lagrange's equations. But the reason we'll be interested in Hamilton's equations is that when you go on and learn about quantum mechanics, the Hamiltonian and Hamilton's equations is what will become fundamental. Something known as the Hamiltonian will be your fundamental quantity of interest in quantum mechanics, the way now we'll see the Lagrangian as our fundamental quantity of interest or our fundamental function in classical mechanics. All right, so with that, that's all I want to say in this video, and hope you enjoy diving into all of these exciting new topics.